When we want to move, our primary motor cortex in our frontal lobe is going to send signals to the corresponding muscle in order for us to move. And the way this works is our primary motor cortex is going to send signals through the corticospinal tract, which is then going to synapse at the ventral horn of the corresponding spinal cord level. And so we have these alpha motor neurons, which are then going to receive that signal and then send that signal to the corresponding muscle that we're trying to move. So if we were to zoom in over here, where the corticospinal tract is interacting with the alpha motor neuron, we would see this picture. So the corticospinal tract is going to cause acetylcholine release, which is then going to stimulate the sodium potassium pump. Now we're going to have influx of sodium and efflux of potassium. And so this influx of sodium and efflux of potassium is going to cause depolarization. This depolarization is then going to cause further depolarization by the opening of these sodium channels. And so now we have further sodium influx, which is then going to cause further depolarization. And this is going to then ultimately end up opening the calcium channels. The influx of calcium is important in exocytosis of neurotransmitters. In this case, we have acetylcholine within the vesicles, and this release of acetylcholine is going to be what ultimately causes muscle contraction. So the calcium is going to get into the cell and cause the exocytosis of the vesicles, which release acetylcholine into the synaptic cleft. And then acetylcholine is going to bind to the acetylcholine receptor found on the skeletal muscle. This acetylcholine binding to the receptor is going to then stimulate the sodium potassium channel found on the membrane of the skeletal muscle, which is going to cause influx of sodium, which is going to lead to depolarization. This depolarization is then going to open the voltage sensitive sodium channels, which is going to cause further depolarization. Now we have this further depolarization. This is going to ultimately trigger the L-type calcium channel found on the T tubules to open up. So the T tubules are going to be part of the skeletal membrane. So these are basically imaginations of the skeletal membrane. This is going to be extremely important for the spontaneous contraction of the muscle fibers. So once this L-type calcium channel opens, we're going to have influx of calcium into the skeletal muscle. And this influx of calcium is going to be causing the L-type calcium channel to change conformationally, and this is going to cause it to mechanically interact with the ryanodine receptor found on the sarcoplasmic reticulum. So it is not the direct calcium release, but this mechanical interaction between the L-type calcium channel and ryanodine receptor, which is going to lead to the efflux of calcium from the sarcoplasmic reticulum. So the L-type calcium channel and the ryanodine receptor mechanically interact, and this is going to lead to release of calcium from the sarcoplasmic reticulum. Once the calcium is released from the sarcoplasmic reticulum, calcium is then going to bind to troponin, and troponin is going to then cause the tropomyosin um, to be displaced from the actin, so that myosin binding sites from on actin is open for myosin to bind, and so then myosin is going to bind to actin and then ultimately cause muscle contraction.